We've now moved to that part of the course where we'll begin to discuss density functional theory. In this first video in the series on density functional theory, I want to talk about the fundamentals underlying the theory. And in many of the videos that I use, I'm going to borrow a few slides from my colleague Don Trular with permission, and you see that I took these slides from a talk he gave to the chemistry department at the University of Minnesota in 2009. So, why is electronic structure theory important? What have we been doing with wave function theory up to this point in the course? Well, the wave function, which we're deriving from electronic structure theory, is useful because it contains really all the information about a system. And some of the information we found particularly useful has been, for instance, the electron density, that is the distribution of the electrons, and in a molecule, the distribution of the electrons and the positions of the nuclei give rise to certain important properties like the dipole moment, or more generally a charge distribution. And the electronic energy, once we invoke the Born-Oppenheimer approximation, you'll recall that that allows us to define a potential energy surface, and it's with that surface that we can now talk about things like the energies of geometries and bond energies, barrier heights, equilibria between different minima, and so forth. So, how have we been going about calculating electronic structure up till now? Well, let's take an example molecule, and let's take benzene, for example. And if you go through the calculation, you'll discover that benzene, which is C6H6, carries with it 42 electrons. And based on wave function theory as first described by Erwin Schrödinger in 1925, all the information which is contained in the wave function can be determined from that function, which is an anti-symmetric function. That is, if we were to swap the coordinates for any two electrons, we would get a change in sign of the wave function, so that's something that has to happen with fermions. And it is 42 electrons, so if we think of the spatial coordinates of each electron, there's an x, y, and z, so there's 3. 3 times 42 is 126, so it's an anti-symmetric function of 126 spatial coordinates for the electrons, and the electrons also can have spin, alpha or beta spin, and so there's 42 electronic spin coordinates as well. So that's a function of altogether 168 different coordinates, which, well, that's a lot. And so sometimes this is referred to as the quantum nightmare. And here's the Schrödinger equation we've been talking about. It's very simple when you just write h psi equals e psi. And then if we actually expand that Hamiltonian operator, you'll recall there is a kinetic energy term, and I'm not using atomic units now, so you see masses and h bars appearing. There is an attraction to the nucleus term, so E squared is the charge times charge, and then Z is the nuclear charge, and it's some integration over all space of the distance of the electrons from the nuclear positions. And then the red term, this last term, that's the one that's really quite tricky. That is the interelectronic interaction, so E squared, the charge on two electrons, the distance between the two electrons, and that's electron correlation. So in general, of course, we can think of the Hamiltonian as being generalized into three terms: a kinetic energy term, a nuclear attraction term, or maybe we would call that a one-electron potential term, and then U is the two-electron term, the interaction between the electrons. Well, so let's step back for a minute and think about wave function theory and think about the general goal of trying to get out all the information in a molecular system. So it goes without saying that the generic wave function psi is complicated. There's 4 coordinates, if you include spin, for every single electron, and there can be a lot of electrons in a complicated molecule, so that begins to become quite challenging as systems grow bigger. The wave function itself is relatively difficult to interpret. We can operate on it with operators and pull things out, but if you just sort of look at the wave function, and I'll remind you, it's this sort of anti-symmetrized product of orbitals, and we write orbitals as linear combinations of basis functions. It takes a computer to write down the wave function in sort of columns and columns of numbers. It certainly does not lend itself to an easy, intuitive interpretation when glancing at these columns of numbers. You really are forced to use operators. So we can ask ourselves legitimately, would it be possible to simplify things? Another aspect about psi that's kind of odd is the units on the wave function are certainly unusual, right? It's probability density to the 1/2. So we have to integrate the square modulus of a wave function in order to get probability. So it just seems as though there ought to be some physical observable, that is, some tangible aspect of a system, not something as intangible as a wave function, that would still completely describe the system. And so the question that arises then is, what physical observable is it that might be most useful? And in a sense, working in the opposite direction, one hypothesis would be, well, if we've got a physical observable that allows us to construct the Hamiltonian a priori, which would allow us to do wave function theory, that physical observable ought to have contained within it all the information in the system, because there's sort of a connection to wave function theory that way. Well, okay, and so as we've already mentioned, if you want to do benzene with its 42 electrons, you'd follow Schrodinger's approach, you'd have this very complicated function. But in 1964, Pierre Hohenberg and Walter Kohn proposed a different approach. They called it density functional theory. And they proved, with a theorem that we'll see a little bit later, that all of the information in a system is actually contained in the electron density. So the electron density, of course, that is a very simple function. It is a function of only 3 coordinates. That is, we live in 3-dimensional space. So given an origin and a molecule and its orientation, we can define the density at every position in space as a function of only 3 coordinates. So each of these two accomplishments by scientists in the 20th century was tremendously important, and each was awarded with the Nobel Prize. So Schrödinger published his work on wave function theory in 1925, and he was awarded the Nobel Prize in Physics in 1933. Hohenberg and Kohn published in 1964. Kohn was awarded the Nobel Prize, not Hohenberg, in part because Kohn did additional work, some of which we'll see in upcoming lectures. And Kohn shared the Nobel Prize with John Pople, who won it for practical wave function theory, I guess I would say. So Schrödinger for the development of wave function theory, Pople for making it actually a sort of everyday tool and figuring out how to do that. But in any case, in 1998, Kohn and Pople shared the Nobel Prize in chemistry. So what's up with these calculations in a very fundamental way? If we think about wave function theory, while we've gone into a fair amount of detail on the calculus and the algebra and the matrix algebra that's required to optimize molecular orbitals, nevertheless, we can take a very high-level view and say, ultimately, what we're doing is, we've got some equation, h psi equals E psi, that's the Schrödinger equation, and we are seeking, because of a variational principle, to find that wave function which minimizes the expectation value of the Hamiltonian over the wave function, and hence minimizes the energy. So we can pick trial wave functions, and as long as we find the one that does in fact minimize this expectation value, we must have found the exact wave function, because from the variational principle, we know we can't go below if we have a variational theory. We can't go below the correct energy is what I should have said there. In density functional theory, there is a similar high-level procedure that can be envisioned. So now, instead of a wave function being our trial variable, if you want to call it that, the thing that we are modifying, we have an electron density. And in DFT, what we say is, we're going to minimize this is now no longer an expectation value in the sense of an integral over all space. Instead, I'll just put it in brackets. So minimize the energy, and how do we get the energy? Well, it's the interaction of the density with the nuclei. So there are nuclear charges that are positive, and they interact favorably with the density. And since the density is continuous through space, we have to integrate over all space. And then what Hohenberg and Kohn showed was that there is some universal functional of the density that contains the rest of the energetics that we would need. And that would include, say, the kinetic energy and the electron-electron interaction. So given that functional, which, as I say, Hohenberg and Kohn proved existed, we should be able to try density after density, and when we have tried all densities the one that gives the lowest energy will be the exact density for the system. So, what's the problem there? Well, each of these theories has its own problems. So, in 1929, Paul Dirac, commenting on Schrödinger's wave function theory, noted that, quote, "The difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble." So, now let's come to density functional theory. So we're going to attempt to minimize this quantity by varying the density, but there's a small problem. It's not that the equations are too complicated to be soluble. We don't even have an equation for f. So the Hohenberg-Kohn theorem, which shows that f exists, does not say anything more than that it exists. So it's an existence proof, but it offers no insight whatsoever into what this function f looks like. So that makes it particularly difficult to solve the relevant equations. And so here we have the picture from the classic fable of the blind men and the elephant. We do know certain things about this f, this universal functional. So it has to satisfy certain limits in certain kinds of situations, and that can be regarded as being, knowing something about the trunk or something about the tusks or something about the tail. But we really don't know much about the entirety of this universal functional. And density functional theory research, to the extent that people develop functionals, really consists in trying to get a handle on this function f that will be useful in evaluating this quantity and indeed then have a mapping with wave function theory. So in the next video, we will begin to look at some of the early examples of people attempting to define useful functionals of the density that do provide useful chemical information.